optical activity. You can find my entire chirality video series along with a practice quiz and cheat sheet by visiting my website leahprasad.com/chirality. In the video series, we discuss how R and S are chiral molecules that are mirror images or enantiomers to each other, and if you have a solution that is just R or just S, that is considered to be an optically active solution. But when you mix them together into a single solution, you get what is called a racemic mixture. But why is it called optically active? If you look at the word, optics should remind you of your eyes or light. What does chirality have to do with light? Or the better question, RNS is what we discuss on paper, but how do you actually test this in a lab, or how do you actually determine if a solution is pure or racemic? One way to tell chiral molecules apart is by identifying how they rotate plane polarized light in either direction. Which brings us to polarimetry. Polarimetry is how we measure optical activity, but the actual device is called a polarimeter. And if you look at the word carefully, you get polar, which has to do with light, and meter, which has to do with measuring. Light is how we measure optical activity of chiral molecules. Think back to general chemistry or even physics when you learned the topic of plane polarized light. Remember that light can exist as a particle or a wave, and if we look at it as a wave, it oscillates up and down, but in one direction. So notice here it oscillates up and it oscillates down, but if we were to look at it head on, all we would see is straight up and down, and that's in one direction. This is sometimes referred to as monochromatic light because we're looking at light in one color and one wavelength. But if you look at something like a light bulb that is lighting up a room, it happens because the light waves are coming out in every direction. So each wave that's coming out is oscillating in one specific plane. But overall the light is going in every direction, and that's how it lights up a room. When we want to use light to measure optical activity, we need it to be going in one direction, because if it goes in one direction and something makes it turn, we can clearly see that turn happening. But how do you get plane polarized light in just one direction? What we need to do is place a filter in front of the light. So imagine that this is a filter that has a tiny little slit in one direction. So when the light is hitting it in every which way, only the light oscillating up and down in the direction that allows it to pass through the filter is able to continue on. This is how we isolate light traveling in just one direction so that we can test it on the chiral molecules. Here, light in every direction, but here it's polarized, oriented in one direction, or simply plain polarized light. Why is this so important? Because a chiral molecule, whether R or S, is going to have the ability to turn light in one specific direction. This is characteristic of each type of enantiomer because the way that it turns light is going to be very specific to the R version or S version of that specific molecule and change from molecule to molecule. For example, R2-bromobutane will be different than R2-bromopentane. Each will have its own characteristic signature of how it turns light. Imagine you're looking right here and you're seeing light coming at you in just one direction. And when the light that is oscillating up and down hits that molecule, the light is going to turn very, very slightly so that now it oscillates at a slightly different angle. Still up and down, but notice there is an angle right there. And if it hits more of the same molecule, it can rotate more and more and more. If a chiral molecule rotates light to the right or clockwise, that would be a positive rotation, and that is called dextrorotatory or derotary, where derotary means it turns light to the right. In fact, D-glucose is actually called dextrose because it is derotary. If a chiral molecule makes this light turn to the left or counterclockwise, then this molecule would be considered a negative rotation, negative counterclockwise, or levorotatory or L-rotary. Be very careful when you're memorizing these definitions because positive and negative D and L have nothing to do with R and S. When we look at R and S, we rank the substituents, we put number 4 in the back, cross it out, draw a path from 1 to 2 to 3. That is strictly a ranking system for a molecule on paper. But you can have some molecules that are R positive dextrorotary and other R molecules that are negative or levorotatory. So R and S does not equal positive or negative. They are completely different ranking systems. So let's put this all together and understand how the polarimeter works. Picture the polarimeter as a small tube that has a liquid sample in it, and that sample contains your chiral solution. On one end of the tube, we have the light coming in, and just imagine that the light is coming in that one direction where it's oscillating at whatever degrees it starts out, but consider that to be your 0 degrees, your starting point. So if we look at it head on, going in, say this right here is considered my 0 degrees. As the light enters the solution, traveling in that plane path, that one plane, it's going to hit the chiral molecules in solution. And when it hits a chiral molecule, it turns slightly, and it turns slightly, and it turns slightly. And by the time the light comes out the other end, having hit enough of that one type of chiral molecule, it will have turned. So imagine that when it comes out, instead of seeing the light in the up and down position at 0 degrees, it now comes out at some other angle, because the entire plane of polarization is still plane polarized, it's still one direction, but that direction is now at a slightly different angle. When you have a pure chiral sample, meaning a solution that is optically active, it's going to turn it in one direction or the other, where enantiomers, being opposite, are going to turn it in opposite directions. For example, if we look at 2-bromobutane, we can put the bromine forward on carbon 2 or back on carbon 2, where the one on the left is R2-bromobutane and the one on the right is S. This specific molecule, based on lab experiments, has been proven when put into a polarimeter, the R sample of 2-bromobutane comes out to be a negative value. So what would the S sample be? Remember, enantiomers are equal but opposite, so whatever number you get for R, you're going to get the exact number for S, but the positive value. Which means that R is L-rotary and S is D-rotary for this specific example. Don't worry, we'll look at math in the next video. What happens if I put a solution that has 50% R and 50% S into the same polarimeter? As the light is traveling through, the R molecules are attempting to turn it to the left, but the S molecules are attempting to turn it to the right. So the light will hit R and turn to the left, and hit S and turn to the right, and R and S and R and S. And because the concentrations of both are the same, because it's a 50-50 mixture, the net result is going to be a 0 degree change. It comes out exactly as it went in, because a solution that is racemic is considered optically inactive. Not because the molecules don't work, but because they're fighting against each other, and every right turn gets canceled out by a left. They're sabotaging each other for a net result of no change. It's not just racemic mixtures that give you no turn. Achiral molecules are also considered optically inactive, because if they have no chiral center, they don't turn right. So you wouldn't know if it's racemic or simply achiral if you have a 0 degree rotation. But if the mixture is not quite racemic, meaning you have R and S, but you have more of one or the other, you're still going to get some rotation. And this brings us into the math for observed and specific rotation, which we're going to cover in the next video. You can find this entire video series, along with the chirality practice quiz and cheat sheet, by visiting my website, leahforsci.com/chirality.